In this lab, we'll use a serial manufacturing line, similar to the line that we saw in the previous lab, except in this case we have 4 servers. And our interest for this lab is to do something called capacity analysis. In essence, what we're interested in doing is determining what the capacity of the system is, assuming that we have non-infinite buffers between workstations. And so what we'd like to be able to do is determine the impact that changing the buffer size has on the capacity of the system. So another interesting component of a capacity analysis is that we're assuming that we have an infinite supply of parts. So we have an infinite supply of raw materials waiting in front of machine 1, and we have an infinite demand, so we can use all of the parts that the system makes. For our initial model, we'll assume that the processing times at each station are exponential with a mean of 1 minute. And so again, we're also assuming that we have finite buffers, capacitated buffers in between stations. And so for example, if M1 is finished processing and M2 is busy and the buffer is full, then M1 will be blocked and you can't continue, or you can't start processing another part. Similarly, if M1 is busy, the buffer between M1 and M2 is empty, and M2 is finished, then M2 is starved. So it's available, but there's no work for it to do. And so as we'll see, the inclusion of capacitated buffers is going to cause a capacity loss caused by the blocking and starving effect. And so the two things that we need to do differently than we've done in our previous model is handle this infinite supply and deal with these capacitated buffers. So let's look at building this model. So the first thing we'll do is open up Simio and drag our source object and our 4 server objects. So I'm going to use multi-place here. So there's server 1, server 2, server 3, and server 4. Escape out of multi-place and place our sink down at the end. And so I'm going to, for this model, use connectors. So I'm going to go grab the connector object again in multi-place mode, place my connectors in between my stations to make my serial line, and escape out of multi-place mode. I'll grab my default entity and let's rename it parts, and then let's also go through and rename our servers M1, M2, M3, and finally M4. And at this point we can run our model. We haven't changed any of the parameters, so as usual we expect the servers to all be able to keep up with the output from source 1. Let's go ahead and turn the arrows off since we know the direction of part flow. And let's also use entity symbols like we saw in the last video series so that we can change the look of the entity as it flows through the system. So if I zoom out, we know that we have the symbol list, and so it starts out with entity symbol index 0, and it'll be 1 when we leave M1, 2 when we leave M2, 3 when we leave M3, and 4 when we leave M4. So we need to add those corresponding symbols. So we'll add symbol 1, 2, 3, and 4. And so you can see we have our 5 symbols starting with the 0 index. So we'll grab the first one and or make the first one active, and we will go through and change the color. So we will make symbol 1 red. We can make symbol 2 dark blue. We can make symbol 3 purple. And finally we will make symbol 4 light blue. So as you recall, using symbols is this two-step process. The first step is in defining the symbols, which we've just done. The second step is telling Simio where to use the new symbol index. And so as we did before, we will use the state assignments, and we'll use the state assignments for before exiting. So right before the entity exits the server, we will add a state assignment and set the model entity.pictureState to a value of 1. and then we will set the to a value of 2 on server 2. So model entity picture a value of 2. When it leaves server 3, we will set it to a value of 3. So model entity picture 3. And finally, when it leaves server 4, we will assign a value of 4. So we add our assignment, model entity picture a value of 4. And so now when we run our model, we should see the entity changing colors as it moves through the system. So we are updating the entity state, entity symbol as we design. The next thing that we'll do for our model is we will update the server processing times. So recall that the server times, or the processing times at each station, is exponential with a mean of 1 minute. And so we can set those. And what I'm going to do, since they're all the same value of the property, I'm going to use multi-select. In other words, I'm going to select M1 and hold down the control key, select M2, M3, and M4. And then I'm going to open the processing time property, and because I have all 4 selected, it will let me set all 4 property values to be the same thing. So we're going to have random, exponential, with a mean of 1. So exponential with a mean of 1. And make sure that our time units are minutes. So we're going to, before we talk about the source, I want to show one other thing here. So I'm going to set the run length to be 200 hours and run my model. And we will see immediately that parts are arriving faster than we can process these. The source default property arrives at the rate of 4 a minute, and each processing station can only process at the rate of 1 minute. And we can see this if we run in fast forward mode. And if we run long enough, we get this Simio runtime error that says the maximum number in system limit for object of type parts has been exceeded. So let's take a look at where this error is coming from. So we have this property value, maximum number in system, set to 2500. So I'm going to pause the simulation, actually stop it. Select parts, the parts object instance, and then go down and look at the population category for properties, and we can see this maximum number in system property. And so this property is an aid in debugging program, or debugging your model, because it's just saying that if you exceed this number, Simio is going to warn you with the warning that we just saw. And it's a pretty safe bet, unless you have a highly specialized model, that when you get this warning, you're getting the warning because you don't have sufficient capacity, and that the entities are arriving or building up somewhere in the system, and there is a mismatch in arrival speed and processing speed. Of course, since the maximum number in system is a property, we can always change this value. So if for some reason it's not an error for me to have 2500 entities in the system, I can change this value to say 3500, and when I run my model, now it will continue to run further. And so now we've run till we have 3500. And so we could continue increasing this, but again, it's a pretty safe bet that there's a problem in the model. And of course, in this case, we know that that parts are arriving faster than we can process them, because we haven't addressed the arrival process. We just used the default values. So let's have a look at this arrival process and figure out how we should characterize the process, how we should characterize the arrival so that we can do our capacity model. So recall what we have in our source is we have an in-arrival time by default. Parts arrive according to an in-arrival process, where the in-arrival times are exponential with a mean of 0.25 minutes. And so essentially a part arrives, we sample from an exponential distribution, and at that point in the future, the next part arrives, then we sample again from the distribution, and so on. So we're using this self-regenerative arrival process. This isn't really going to work for our capacity model because our capacity model assumes that we have an infinite supply of raw materials. So we really don't know what the arrival or what the arrival time is. In fact, what we'd like to have happen is for there always to be a part available whenever M1 is ready to process the part, but we don't want to have a large queue of parts because a large queue of parts waiting in front of M1 because that will impact the number and system statistics that we're collecting. So what we'll do is we will use a different arrival mode for our source. So if we go over and look at the arrival mode property, the default value is the arrival time. If we pull on or click on the drop down box, the one we want is this on event. And so when we do that, it brings up an error saying, okay, well, you've chosen an on event arrival mode, you need to specify the event. And then if I click on my source again, you can see that I have the error here because I don't have a triggering event. So before we choose the triggering event, let's talk a little bit about more detail about how the server object works. And so basically we see that we have a input buffer, we have a processing queue, and we have an output buffer. We have an input node and we have an output node. And so when we select one of these items, you can see, or one of the components of the server, you can see its name and its object type. And so we have the input buffer, the input node is a basic node. Then we have the server and we have the output node, which is a transfer node. So when part arrives on the connector, it looks for available space in the input buffer, and if there's available space, it exits the connector and waits in the input buffer until there's sufficient capacity for processing, at which point it moves to the processing station. When the processing time is complete, it looks at the output buffer to see if there's capacity, and when there is, or when there's capacity at the on the connector, it leaves the processing station and exits through the output node. So what we want is we want to trigger an arrival from the source when an entity leaves or successfully exits the output node, because when that happens, we know there's sufficient space at the downstream station, in this case M2. As soon as the part can exit the node, we know that there's space either in the buffer or in the processing station at M2, and we can then start processing our next entity. So on our source, I'm going to go and I'm going to click on the drop down. And now instead of having the generic expression builder, we have just a list of all of the events that Simio knows about. And so what I'm going to do is I'm going to look for the output at M1, and you can see these are the events that are associated with the output on M1. So we have a capacity change, entered, exited, write, or waiting event. And the event that we want is this output at M1 exited. And so this event is fired when an entity leaves the output node. In other words, the exact time that we want to create a new entity. So with the on event arrival mode, when this event occurs, when one part leaves, we create the next part. The only thing we need to do to get the process started now is to create an initial entity. So we create an initial entity at time 0, and it immediately starts processing on M1. When capacity is available, when the processing time is completed and capacity is available at M2, the part leaves, and as soon as it exits the output node, we create the second part. So if we watch this happen, what we should see is that there is always a part being processed on M1. So let me speed up the animation a bit, speed it up quite a bit actually, so we can see the process working. And you can see that we always have the green entity at M1. We don't always have entities at M2 or M3 or M4, but we always have one at M1. And so we've achieved our goal of having, in essence, an infinite supply of raw materials in front of server 1. And it's important to understand the difference in the arrival mode uh, from what we've seen previously. So previously we have had random arrivals where we define the inner arrival time. So we have a random process that we're sampling, and we in essence don't know when an entity is going to arrive. We have information about the distribution, but we don't know when it's actually going to arrive. With the current model, however, we specify when an entity arrives at the exact time when it departs station M1, and so the net effect is that instead of having random arrivals, we always have a part available, so we have our infinite raw material supply. And we're doing that with the exact same source node or source object from the standard object library by just changing this arrival mode. You can also see that there are two other arrival modes, the time varying arrival rate in the arrival table, which we will see both of those in subsequent labs. So the last thing that we'll do in this video is we will define our experiment and our standard responses. So the responses that we've looked at before for our queuing type systems are the utilizations of the servers and the number of parts in the system and the time that a part spends in the system. So let's go ahead and define those. So our first response is going to be, let's name it M1 util for M1 utilization. And recall from the previous video, this is going to be M1 capacity scheduled utilization. And we will do the same thing for M2, M3, and M4. So M2 util is, we can use the expression builder this time, M2 capacity scheduled utilization. M3 util, and again use the expression builder, M3 capacity scheduled utilization. And finally M4 util, will be M4 capacity scheduled utilization. So we have our 4 server utilizations, and we'll add the number in system, which we will abbreviate as NIS. And recall this is based on the parts object instance, the population, the number in system average. So parts.population.number in system average, and time in system we'll use the same parts population time in system average. And with the time in system we will also specify time units, and let's display time units in minutes since we have 4 individual servers and each one the average service time is 1 minute. We will also report the time in system under minutes. And as the last item, let's set the warm-up time to 100 hours. So we have replications of 200 hours with a warm-up time of 100 hours, and we have our 4 utilizations, our number in system and time in system. Before we run our model, run our experiment actually, we should think about what we expect to get. Recall during the modeling, we should always ask ourselves this question of what we expect to get so that we can reconcile our expectation with our model results so that we can do verification as we build the model. So if we look back at our model, we have the arrival process defined so that M1 is always busy, and so we would certainly expect M1's utilization to be quite high, probably 100%, since there's no time when it should be idle. And similarly, we should also expect M2, M3, and M4 to also have quite high utilizations, because in the default mode, since we haven't said otherwise, we still have infinite capacity buffers between all stations. In other words, we have the input buffer to M2, M3, and M4 are all set to infinity because we haven't told Simio otherwise. So let's go ahead and run. Again, we have 200-hour replications with a 100-hour warm-up. And as we run our model, take it just a few seconds to run each replication. We can see as we finish replications, as we expected, the M1 utilization is exactly 100. It's always busy. M2 utilization is quite high. M3, M4, all of the utilizations are quite high. Correspondingly, the number in system is also quite high, and parts spend a fair amount of time in the system. Recall there's approximately 4 minutes of processing time, and the average part now is spending approximately 275 minutes in the system, and so they're waiting in line for an awful long time. In the next video in this lab, we will look at how to add finite capacity buffers between individual stations so that we'll no longer have the infinite buffer size. And we'll also look at how to compare multiple scenarios using different buffer configurations.